Okay, today we're going to talk about the rules of the game, the fundamental principles of probability. They are actually just three. They are called the axioms of probability. They are very simple, but the entire body of knowledge of probability is actually based on these three. And from these three, they are what you call the consequences of these axioms, and it's what we build upon. So maybe a brief history about the axioms. This field of probability has been there for really so many years, so many centuries, but it was until 1933 when someone called Komogrove put together these three axioms to sort of give unity to this body of knowledge. Because before that, people used to calculate probability and get different answers, and they didn't have like a way of figuring out if the answer is correct or wrong. So if you're beginning in your journey of studying probability, this is going to really be very helpful, because it's sort of like the way you would be able to prove whether your answer is actually wrong or right. So I'll start with the very first axiom. So the very first axiom is called non-negativity, which really is very simple. So axiom 1 is the non-negativity. So this axiom is such that the probability of any event, call it event A, is greater than or equal to 0. So like you cannot say that the probability of something happening is negative 0.5. Like that's not really possible. I'm just going to first state them, and then don't worry, I'm going to jump into all the rest. So the second axiom is normalization. Call it. So the normalization axiom is basically saying that the total overall probability, the probability of the entire sample space is 1. And in mathematics, we denote the sample space by this symbol omega. So the probability of the entire sample space is equal to 1. And then the third axiom is that we call it countable additivity. Right? That is countable additivity. So let me expand on each of these. Of course, now this one is just intuitive, you've already understood that. And then this one, let's say, just imagine this is our sample space. And in this sample space, let's just consider just two events. Let's say event A, and then maybe there is event B. So this is event A, and then this is event B. So, and then maybe what's outside here is whatever is not in A and B. The total probability of all this is 1. There's no need to prove that really. There is no mathematical proof for that. And then countable additivity is, let's say you have, let's say this is your sample space, and you have, let's say this is event A, and then there's also event B. Let's say this is A, and then this is B. So if they have no intersection between them, then the probability of A union B will simply be the probability of A plus the probability of B. But then so this is really countable additivity is what we call, from these three axioms, you may be wondering why there is, like, the list is not longer. The thing is, the other things that you already know about probability, which I'm going to write here, can actually be derived from only these three axioms. For instance, for the countable additivity, you are having event A and event B. And now, like, you see these events have no intersection, so their union is simply the sum of those two events. But then you can have event A is here and event B is here, and they have an intersection. Let's say this is A and this is B. So if they have an intersection, the probability of A union B will be equal to the probability of A plus the probability of B. But then this, let me actually shade it. let me use a bigger thing. Like this is event A and this is event B, and that's the sample space. So let's say this is event A and this is event B, and event A takes place here, event B takes place here. So you will notice that this intersection happens to have red lines and green lines. That means the intersection occurs twice. That's why we have to remove it once, because it has been added one more unnecessary extra time. So this will be minus the probability of A intersection B. Okay. So another consequence of probability is that you can have, let me create for myself more space. You can have, let's say this is event A and this is our sample space. So the total probability of all this is this is the complement of A. So that means the probability of omega, the sample space, is equal to the probability of A plus the probability of A complement. But we know that this is equal to 1, that's probability of A plus probability of A complement. And then we get the probability of A is equal to 1 minus the probability of A complement. And many other axioms consequences can be derived from this. The other consequence that is commonly talked about, not just commonly talked about, but really important when you're doing your calculations, you really want to, or when you design a probabilistic model, you always want to do something called a sanity check. So you always think about this. Like, let's say if you have that the event A is a subset, that means a subset of B. That is something, for instance, like this. So you have event A here. Okay, let me use another illustration than that. Let's say you have, let's just say this is the event B. It's our entire sample space. And inside there you have, this is event A, and maybe this is event C. So the probability of event B is going to be equal to the probability of event A plus the probability of event C. And this clearly just states that definitely this has to be, if this is a subset of this, that means the probability of B is greater or equal to the probability of A. Any other, probably one more thing to talk about is, let me just create some more space, just a second. So you can have, I first started by drawing, I said this was event A for countable additivity and event B. And yeah, so this actually maybe something I should highlight is that event A and event B in this specific case are mutually exclusive events, but that does not necessarily mean that they are independent. You get, because if I told you the probability of event A, if I told you that event A happened, they are mutually exclusive. If I told you that event A happened, that means event B cannot happen. Well, that's something we shall dig into later. Let me not go into that. Let me just work an example applying all these axioms, and then we shall finish.